Hello, friends. This is Uncle Sam again, and today we'll be moving to the episode 2, and this is the time we'll be talking about, or we'll be solving, or we'll be explaining second order ODE, second order ordinary differential equation. And this time around, we'll be dealing with homogeneous linear ODEs with constant coefficients. I'm going to explain further on what I mean by that. Um, so I'm looking for the pen. Um, okay, the topic will be homogeneous homogeneous linear ODE with constant coefficients. What do we mean by this? We have our y prime prime plus ay prime plus by equals 0. Why is this equation homogeneous? It is homogeneous because our value, or let me say variable, that is supposed to be different from the y terms is equal to 0. For instance, if you have this as 5 or you have this as x squared or something different from 0, then it is non-homogeneous. So, but right now, because you have this as 0, it is homogeneous. And why is it linear? It is linear because our term of y is not in power of anything. If this y prime prime, um, second order, is in power of, let's say, 2, or this is in power of 2, or you just have like a term of y connected to another term of y in terms of multiplication or division, then it is a nonlinear ODE. If you have, let's say, y, let's say you have y prime, or you have just, even if it is just y here, it is non-linear. So for this particular question, you have this as homogeneous linear ODE with constant coefficient. And also, what do we mean by the constant coefficient? All these are the constant coefficients. They are constants. They are not x. Let's say if you have x here, you have x squared here, then this has turned to non-constant coefficient. So this is a constant coefficient. So let's put it together. We have homogeneous linear ODE with constant coefficient. This kind of ODE can be solved, or let me say it has three cases, and we'll be explaining each of the cases one after the other. For instance, um, okay, let me write out. As we all know that the solution, for example, so before we go to the cases, let me explain this. The solution of y prime plus ky equals what? 0 is y equals c, like this is the constant, raised to power minus kx, which can also mean what? Y equals what? E raised to power gamma x. If you represent minus k as gamma, and um, don't let us work with c yet. So we're trying to derive something. When you have y equals to e raised to power lambda x, I want to be able to see what your lambda would be for this particular ODE. You're trying to change your order, like the second order in terms of y, this in terms of y, and so this will actually help you in getting the general solution. Uh, or let me say the solution. When you have y as this, your y prime is going to give you what? If you remember, if you want to differentiate this, you differentiate this and you differentiate as a whole. You have lambda e raised by lambda x. And if you want to differentiate this again, equals what? Lambda again will move forward. So you have lambda squared exponential lambda x. And you can put that into the equation of the ODE we have there. You have this as, you have y prime prime first, lambda square e raised to power lambda x and plus a y prime. Then you have what? Plus a lambda e raised to power lambda x. Then plus b e raised to power lambda x equals what? 0. You can bring in lambda ex out. Lambda square plus a lambda plus b equals what? 0. This can be 0 or this can be 0. So lambda square plus a lambda plus b equals what? 0. Then you can use a quadratic form of general equation to solve for your lambda. If you remember this kind of equation that says x equals what? Minus b plus or minus no b squared minus 4ac over 2a. If you remember that kind of quadratic equation, we're going to apply the same thing here, but just that the arrangement is kind of different in this kind of situation. But you need to recall that formula, and this will give you what? Lambda equals minus a plus or minus, because instead of this being your b from the quadratic equation we are used to, it's going to be a here because this is the coefficient of lambda, plus minus root of a squared minus 4 1 times b over 2 times 1. Lambda equals what? 1 over 2 minus a plus or minus a squared minus 4b. If you're trying to get your lambda, the kind of solution you're getting for your lambda will depend on how your general, or let me say how your solution is going to look like. If so, that's where the cases now comes in. If you get your lambda, for example, let's talk about, okay, so when you get your lambda, normally it should be like y1 equals what? E, that's exponential, raised by lambda 1 x, because it's a quadratic equation. You've gotten plus or minus, so your first value will be your lambda 1 and the negative part of it in the equation will be your lambda 2. You have this, and y2 equals what? E raised by lambda 2x. Then you can add this and this together. This will make your general to make your solution. And yes, then from there, if you're given your initial conditions and the boundary conditions, then you can find a general solution. But we're not there yet. But now you've been able to arrive to your y as a function of x, or let me say solving y from your ODE question, ODE equation. So for the case one now, when for the case one, we call this 2 real roots. That's when you solve for this and your value of, let me say, this, right, is greater than 0. Maybe when we start solving questions, you understand that better. So it's just you saying a squared minus 4b is greater than 0. Then your solution is going to be y equals c1 e exponential lambda 1x plus c2 exponential lambda 2x. That's that for the case one. That's when you have real roots. Let's say you're able to get your gamma and you get gamma to be like gamma 1 is like 2 and gamma um, 2 is like 4. Then you can put these values directly into this equation. You'll be able to get your y from the ODE.